The next group is going to be the MeltingAsphalt from Computational Tools for Climate Science, and they're going to present temporal and spatial dynamics of heat wave wildfire relationships over Africa. Thank you, guys. Please, I'll leave the stage to you.
Okay. So, hello everyone. Apologies in advance for any background noise from my side in case it comes. So, thank you for being here and with us today. So, we are MeltingAsphalt and we are going to talk about wildfires in Africa, unraveling the hidden crisis of heat waves and wildfire. So, this work has been done under the mentorship of Dr. Daniel Hagan and Dr. Kenny as part of Climate Match Academy. Next slide. So to start with, what are the drivers of wildfires or fires in general? So this is a fire behavior triangle, and we see three major parameters: fuel, topography, and weather. And we know that fuel, any type of fuel in terms of your live or dead vegetation, is something that is a supporting material and a reason for fires to occur. Weather influences fire through effects of wind, air temperature, and humidity. And topography can influence the speed and the spread of the fire. So all these factors together modify the behavior of the fire, speed, direction, and the flame characteristics. Especially in tropical Africa, these factors come together in unique ways. For example, in the north of Africa, we have savannas, which are an abundant fuel as it's a grassland, and in dry season, human-lit fires are common there. But what's changing in this is the climate. As we know that the rising temperatures, there are longer dry spells and more extreme heat waves. Next slide, please. So why are fires in Africa matter? So Africa is the epicenter of global fire activity. While it covers only 20% of the global land area, it actually contributes to 70% of the global burnt area. And in addition to that, half of all carbon emissions is coming from Africa. So put it in simple words, maybe it's a way to visualize it. So Africa's fire release is as much releases as much carbon as the entire EU's fossil fuel emissions in some years. But why does it matter globally? Because these fires aren't just local, they are a part of Earth's carbon cycle also. The emission accelerates the climate feedback loops, and the loss of the biodiversity and vegetation impacts the rainfall patterns. Next slide, please. Another reason is that beyond the numbers that I mentioned before, it has profound impact on the human and ecological costs. For communities, fire destroys crops, displaces people, and worsens the air quality, leading to the respiratory problems. And ecologically, the repeated burning of the land can degrade the soil and make it harder for the forests to regrow back. So one example of the ecosystem is Miombo woodland. Sorry, I always say wetland. So it has adapted to the fire effects there. But if the fire becomes more intense and frequent, it may tip to a level where it's irreversible it will be difficult to reverse the damage. So it isn't just about environmental issue, it's about food security, health, and also the climate justice. Next slide, please. So what is our working hypothesis? So our hypothesis is, do the long-term changes in heat wave frequency modulate wildfire risks in tropical Africa? So globally, we know that heat waves dry out the vegetation and make fires more likely. In Amazon or Australia, this relationship is clearly established, but Africa's fire regimes are slightly different. So we hypothesized that, like, if the heat waves are rising, then proportionally the wildfires also should rise. Next question, next slide, please. And next point was, when and where do we look at? So this is a map from 2015, of the fire hotspots. And if we see that the colors starting from gray, black, dark red, and red are the regions in the north of Africa, and these are the months that's when the fire occurs in this region, and the other colors are the ones where the fires occur in the south. So the two regions have different fire seasons. So we focus on these two regions, north and south of the equator. And our study period is 2003 to 2019, which is chosen based on the overlap of the reliable data set from MODIS and the climate records from ERA 5. and it's long enough to and recent enough to help us show the meaningful patterns. Next slide, please. So the tools that we use are ERA5 reanalysis. We extract surface temperature at 2 meters, and we use this to calculate our heat wave characteristics. And we calculate the vapor pressure deficit using surface temperature and the humidity. MODIS fire data gives us idea about the active fire counts and burn area. And the standardized precipitation evapotranspiration index helps us isolate the drought conditions to filter out the periods when fires are likely to happen. Next slide. So how did we analyze the data set? The first step was we aggregated the data to annual and monthly time series. Then we went ahead and calculated the heat wave characteristics. We used the standard definition of heat waves where we define at least 3 consecutive days where the temperatures hit the top 10% of the top 10% continuously. And then we calculate the vapor pressure deficit. The next step is to look at the relationship between these different variables. So we do it through using Pearson correlation and information flow method, which can be used to establish the causality. And we focus basically on the dry conditions. Now I hand the floor to Frank for further discussion on results.
Okay, thank you, Sadhvi. Sorry, let me just make sure I focus. Yep. So the first thing we looked at is what happened to heat waves over Africa. And we can see that clearly over our study period, the heat wave frequency has increased significantly. This graph is showing the amount of heat waves, basically the area under heat wave conditions in all of tropical Africa. We've seen the same results for the South and North study regions that we've shown earlier. So this is exactly what we would expect to happen under global warming. So no surprises here at all. But if we actually look at fire activity, we've been surprised to see that over the same time period, fire activity in both regions has significantly declined over the same time period. The upper graph shows the burned area, basically how much land area has been burned away by fires. The bottom graph shows the number of fires that happened. In both cases, we are looking at annual data and at the spatial averages over our study regions. So this was surprising because from other studies that have been carried out in, for example, Europe, South America, or Australia, we know that there's a clear relationship between heat waves and fire activity, but we did not see this in the large-scale aggregated data. So in addition to this, we also looked at the grid level. So basically at each grid level of our data sets, we calculated a monthly time series and then calculated the linear relationship between, in this case, heat wave frequency and fire counts. During our study, we also looked at other metrics and didn't see any other results, which basically are showing us that there's no statistically significant relationship between those variables. And then we also did an information flow or causality analysis. And again, we see here that we do not see any significant information flow, only in very isolated spots. And even do we reach 90% significance level? And even if we do this, the actual information flow values that we see are pretty small. To get a deeper insight into what is going on, we looked at various environmental parameters and are showing one example here. So on the left-hand side, again, we see the burned area over the northern and southern regions. And then on the right-hand side, we are looking at the standardized precipitation and evapotranspiration index, which is basically a measure for droughts or drought index. And we can see that in the northern, and this index is to be interpreted in that way that more negative values mean drier conditions. So for the northern region, we see that it has become very slightly drier, and the southern region has become a little bit wetter over the time period that we are looking at. This is a result that we have then confirmed by looking at other studies, and in particular, we want to highlight Supova et al., And this is the 2019 paper who looked at declining fire activity over Africa. And they have shown that about 70% of the decline in burnt area can be explained by increased precipitation. And we can also see nicely here that the northern and southern areas have slightly different trends. The north has been getting wetter than the south. And yeah, of course, when we're looking at effective rainfall trends, and effective rainfall is basically how much rain has fallen minus how much has then evaporated again or transpired again from the land surface and vegetation. So we get like basically a net water that's available, and the wetter the land gets, the less likely it is to burn, I guess you could say. Okay, what are the key takeaways of our study? We've seen that heat waves are definitely up, which is consistent with global warming, which is exactly what we would expect. But surprisingly, we've seen that wildfires are down over Africa in a significant way, telling us that there's no simple relationship between heat waves and wildfires for the regions that we studied. There must be other factors at play here. This has been unexpected from our point of view, but we've seen since then that other studies have actually shown similar results and have indicate that in recent times over Africa, atmospheric and land processes are starting to decouple. And of course, more research is needed to exactly figure out what is going on here. Our studies did have some limitations. First off, the MODIS satellite data that we use to detect fires is known to undercount small fires. There have been comparisons between the MODIS data and the more recent Sentinel data, which has shown that fires below 250 meters in extent are severely undercounted in MODIS. Unfortunately, the Sentinel data is very recent, so we don't really have a long enough time span to use that. And we also only looked at a number of factors that impact fires. You may remember the fire triangle that we looked at the beginning, where atmospheric conditions like heat waves are just one factor that play a role. The scope did not allow us to look at other processes like land use changes or human activity. And related to this, our methods may not have been sufficient to tease out the more complicated relationship than just linear relationship between heat waves and wildfires. And lastly, the standard heat wave definition that we have used may not have been the most suitable one for our study area, but there is like dozens of those definitions out there. And again, the scope did not allow us to find out which ones would maybe be more suited to do this type of analysis. Finally, we'd like to thank our mentors, Daniel and Kenny, for their support and for their valuable feedback throughout this period, throughout the project. And we definitely also want to thank Climate Match Academy for giving us the opportunity to do this and for the support they've given us. And finally, we'd like to thank you, the audience, for giving us your time and listening to us. And we are now able to take any questions that you may have.